Okay, so this is part 3 in solving that sample problems that just encountered. Okay, so I just wrote it here, the bending moment formulas that we managed to derive from the method of sections. And from here on, we need to assume the measurements of each section. As you can see here again, in this free body diagram that we have, this one, from section A-B is equals to 2 meters. So our limit should be coming from A to B. So that should be from 0 to 2 meters because that is section A-B. And then for section B and C, it should be this measurement from A to B and then from B to C because we are only going to utilize the measurement from B to C, right? Then same thing goes here for section C-D. We need to use this measurement and for the whole measurement of this beam. So let's try to set the limits by starting from section A-B. So if let's assign our limit from A to B. So from 0, because we are starting from A, all the way up to 2 meters, which means to say that we're going to assign for x because this is the indefinite measurement that we managed to obtain from cutting the beam in sections. So if x, we are going to start at 0. If x is greater than 0 but less than 2 meters, right? Because we are at section A-A. So this one, section A-B, at this cut at 1. So by using that limit from 0 to 2 meters, so from this all the way to 2 meters, we're going to somewhat solve for m sub a. So m sub a is equals to 18, substitute by 0, so m sub a is equals to 0 kilonewton meter. So that's the first one. I'm just going to use that. And then we are going to substitute for 2 meters. So m sub a is equals to 18 multiplied by 2 meters. So that should be m sub a equals to 18 multiplied by 2 is basically 36. So that should be 36 kilonewton meter. So this is the unit for the bending moment. Okay. So this is for section A-B. So let's proceed to section B-C. Okay. So we're going to consolidate this measurement B to C. So if again, the measurement should be less than this and this measurement. Means to say our limit should be less than 2 meters because A to B is 2 meters and the whole length for this structure. So that should be 5 because 3 plus 2 is 5, right? We are setting up the limits, so that's why we are gonna use this if x is less than 2 but greater than 2 but less than 5 meters because we are already at section B-C, right? We're already done with the section A-B. So m sub b, this is the bending moment formula for section B-C. So 4x, so 4 multiplied by 2, we're going to substitute that, and plus 28 m sub b is equals to, this is 8 plus 28, so 36 kilonewton meter. Then substitute by 5, so m sub b is equals to 4 multiplied by 5 meters, okay, don't forget about the unit, plus 28. So m sub b is equals to 28 plus 20, that should be 48. Yes, the answer should be 48 kilonewton meter. 48 kilonewton meter. Don't get confused with the 28, as you can see here. It still has its unit. It is in kilonewton meter. We just retain the sign because we will get confused. Okay. So for the last one, we are going to consolidate for section C-D. Means to say that this measurement from A all the way to C, that is 5, and then the whole measurement of the beam, so that should be 7. So if x is less than 5, greater than 5 but less than 7, so that is the limit for section C-D. Simplifying everything, I'm just going to simplify that one. This is the bending moment formula for section C-D. So m sub c is equals to negative 24 multiplied by 5 meters and plus 168, that is in kilonewton meter. Okay, don't forget about that. So m sub c is equals to what is 24 multiplied by 5, that is negative 120. Okay, negative 120, the unit is kilonewton meter, plus 168 kilonewton meter. Then m sub cf, x is equals to 5 is equivalent to 48 kilonewton meter. 48 kilonewton meter. And if we are going to assign x is equals to 7, so m sub c is equals to negative 24 multiplied by 7 meters plus 168, that is in kilonewton meter. So m sub c is equals to 24, negative 24 multiplied by 7, that is basically 168, negative 168 plus 168. So m sub c is equals to 0 kilonewton meter. So we already managed to obtain this 6 informations. We have 0, 36, 36, 48, and 48 to 0. So if you can see the pattern here, is that starting from this portion of the beam, from point A, okay, from point A, we started at 0. So, okay, 0. And then for point somewhere at B, from 36, at the end of section A, it became 36, so it's equal. So if x is equals to 5, it became 48. And then solving for section C-D, if x is equals to 5, it became equal again. So equal, and then 48, 48. And then by the end of the beam, which is at this portion, it became 0. So that is the pattern. If your answer is like this, it has equality, like 36, 36. From A to B, 36. From B to C, we have 48 and then 48. And then by the end of this beam, it became 0. So that is the pattern. So after solving for the bending moments for each section of the beam, we're going to construct the shear moment diagram. I'm just going to erase this one. Okay, so let's construct the beam as we have here in this sample. Okay, so this one is the whole beam. Then we have here R sub A equivalent to 18 kilonewtons. Let's just retain the unit. And for this one, we have 24 kilonewton. This one, we have 14 kilonewton. And this one is 28 kilonewton. Okay, So just going to draw straight downward line and two horizontals. And this one. Don't forget about the vertical line that is connecting for 14 kilonewtons. Goes like this, goes downward, and then for 28 also. Because this represents the force that is 28 kilonewtons going downward and 14 kilonewtons also going downward. So this one is V, corresponding for the shear diagram. And then we have also here M, corresponds to the bending moment diagram. So according to our computations, at point A, this is A, B, C, and D. So at point A, we rose up by 18 units of force. So that's why from V, starting from 0, as you can see from our computation just recently that we have 0, diba? Then we rise up by 18 kilonewtons because we have here 18 kilonewtons acting upward. And then all the way to point B, we somewhat need to connect this line A all the way to line B. And don't forget that this is linear because we have no equations that is power to the second power or third or fourth or so forth. This is all linear. And from 18, we rose up from 0 all the way to 18. We're going to move all the way to point B, like this. Then we need to go down by 14 units downward because there is a 14 kilonewton force acting at point B. So we need to go downward. And from there on, this is going downward at this point. So this is 4. Okay, that is 4 because 18 minus 14 is equivalent to 4. And the shear force that we managed to solve at section AB is equivalent to 4 units din, di ba? May 18 doon eh. So pagdating dito kay B, we managed to solve 4 because that is the shear force at point B. Okay, if you can recall in our previous parts. And then let's move on all the way to C, which has a shear moment, rather a shear force equivalent to negative 24. Because from 4, then we need to minus it by 28. So that should be 4 minus 28 is negative 24. And the shear force that we managed to solve at section C is negative 24. So it's correct. So let's move on to C. Then it went down to negative 24. It's like this, negative 24. Then from C all the way to D, connect it, and we'll go back to 0. Okay, so this is the shear diagram, this shaded area. Okay, I'm just going to shade that one. So this is the shear diagram. And last but not the least, for the bending moment diagram, so from 0, okay, starting from 0, we managed to solve for the bending moment from A to B, which is 0 to 36 kilonewton meter. And take note that the formula for the bending moment from A to B is somewhat linear because it's not in squared or cube, so that's linear, so it should be straight. So it goes up, this is 36 kilonewton meter, and then just going to move this one, negative 24, and then from B to C, it managed to go up to 48 kilonewton meter. So it goes up to 48 kilonewton meter. So this is 48, okay. And then from 48 kilonewton meter all the way to 0. It came back to 0. So this is the bending moment diagram for this beam. So that's what you call the shear moment diagram.